Hello, and welcome to our fifth and final section of chapter 7 of similar polygons. Today we are going to be learning about our angle bisector theorem. And as we know what an angle bisector is, in case you didn't remember, it is literally a segment or a line or a ray that divides an angle into two congruent angles, thus angle bisector. So this is our theorem for the angle bisectors. So let's get straight into it. Angle bisector theorem. And ooh, that looks bad. Angle bisector theorem. So I'm going to draw a triangle, and we're going to talk about this first. You'll notice that I do have a triangle right below it already. But if we have, for instance, let's call this triangle A, B, C, and then we're going to put a point D here. Okay, and what I'm going to do is I'm going to take this angle A, and I'm going to divide it or bisect it into two congruent parts. So meaning, I'm going to put one tick, meaning those two angles are congruent to each other. So I'm going to actually write angle BAD is going to be congruent to angle DAC. Or CAD, however you want to do it. Let's do CAD. Okay, so those two angles are congruent to each other. And what happens with this theorem is it takes the adjacent sides, and I'm going to call this adjacent side ADJ. Adjacent means next to. Let's call this ADJ1 and ADJ2 because there are two different perspective triangles here, okay? Meaning adjacent side 1 refers to the left triangle, adjacent side 2 refers to the right triangle, okay? Or the triangle on the right. And we're also going to be working with opposite sides. So the opposite side is this long piece, but we're actually going to break this up into two different opposite sides, okay? And I'm going to call this opposite 1 and opposite 2. Okay. Now, what this theorem states is that we have, when you have an angle bisector, so let's highlight this angle bisector. If you have an angle bisector, it will divide the opposite side into segments, so these are your two opposite sides, into segments that are proportional to its adjacent sides, okay? And that seems like a lot of information, so let's break this down really, really quickly. I'm going to say, right here, I'm going to say, ADJ, adjacent side 1, okay, which is our AB length, or AC length, is going to be proportional to our ADJ2 side, adjacent side 2. And then we're going to follow the same pattern, opposite 1 over opposite 2. Okay, and this is traditionally how I've always shown you this entire chapter. Take the one triangle, its corresponding side, take its side on the left again, line it up with its corresponding side, okay? So in this perspective, we could actually say AB, actually let's do this in the colors again that I used. And let's do this. I'm gonna rewrite this entire equation, but with the actual segment lengths. AB is going to be over AC, which is equal to or proportional to BD over DC. And that is our theorem in a quick nutshell. Now, the angle bisector theorem, let's go ahead and define it. If a ray, let's say put segment or line, bisects an angle of a triangle, then it divides the opposite side. Into segments that are proportional to the adjacent sides. Okay? So, we could think of this, it's very, let me rephrase that. It's very tempting to think about this as similar triangles, but these are actually not. So that's a very important key here, is that they're not necessarily similar triangles. They can be, but they're not necessarily similar, because that's right here. Let's do a subnote, not necessarily similar. Because if we use this angle bisector theorem and we split, for instance, this triangle in half, what happens here is we take this 60 at the top and this turns into 30 and 30, right? But we have two different triangles going on here. Okay? We have the red triangle, which is now 70 plus 30 is 100. And then that means this last angle has to be 80 degrees, okay? This triangle to the right is a 30, 50, 100 degree triangle. And that should make sense because we have a linear pair here. But notice that the blue triangle and the red triangle are not similar because they do not have all of the same angle measures. What this theorem is stating is that it's saying that literally only these sides in particular are proportional. Okay, not congruent, and that's actually bad portrayal on my part. But what it's saying is the adjacent side 1 is proportional to adjacent side 2, along with opposite side 1 and opposite side 2. Okay, so keep in mind that these triangles are not necessarily similar. They can be if we have, for instance, an isosceles triangle. So let's just do a really quick mini example here. Wow, that's a trapezoid. If we have, for instance, 60, that's a bad example. Let's go 70, 70, 40, and then cut this in half. You have 20 and 20, making this 90 and 90. Then this would for sure be similar, but it's not necessarily similar, okay? All right, so that's it for today. Other than that, if you have any questions, bring them to class, and I'll see you in the next one. Bye.